Welcome back for the second part of section 3.2. We will begin with problem number 7. Doing the same thing we did with the problem number 5 and 6. We are going to use the first derivative to find our critical values and determine if we have relative max, relative mins, and intervals of increasing and decreasing. And then we're going to use our second derivative to talk about concavity and possible inflection points, and then put all this together to sketch the graph. So let's start by finding the first derivative. So we're going to find f prime here using our power rule. This is going to give us 4x to the third minus 6x squared. To find the critical values, we're going to take that first derivative and we're going to set it equal to 0. So once again, same kind of practice that we did a while ago in the previous part of this. So we're going to take out a 2x squared because that's our greatest common factor. That leaves us with a 2x in the first term, and looks like a minus 3 in the second part. And so these are going to be our two factors. We're going to take our 2x squared and set it equal to 0. This is going to give me a critical value of 0. And if we take 2x minus 3 and set it equal to 0, we're going to have a critical value of 3/2 or 1.5, whichever one you want to use. I think MyLabs Plus prefers the fraction, but we can list it whichever way you want to. So let's go ahead and find those actual points, and then we'll figure out what to do with them and how to classify them. There's several different ways we can go about doing this, but we're going to go ahead and plug in our x values into our original function. So here we'll have our function evaluated at 0. This one's pretty nice. We get 0 minus 0, so we're just going to get a nice value of 0. So that's one of our points. What it turns out to be, we don't know yet. Our second point is going to be this 3/2 or 1.5. When we plug this in to our function, so if we want to find f of 3/2, you can plug that into your calculator using the fraction version or the decimal version. You should get exactly the same results. I just want you to see how this all gets plugged in, and that will give us the value negative 27/16, which is just a lovely value there. You can rewrite that back as a mixed number if you prefer. When you get ready to graph this, this is approximately, or it is negative 1 and 11/16. Read in MyLabs Plus as to whether they would prefer an improper fraction or a mixed number. So anyway, so our second part here is negative 27/16. So now let's talk about how to classify these. So let's draw our number line from our first derivative. So this is once again our first derivative number line. So here we go. So we're going to put on two critical values. Remember, the only things that go on this number line are our critical values, our x values. And so I'm going to put these, I always put my test points kind of above my number line so I know that that's what they are. So -1, 1, and 2 will all work very nicely. And then we're going to evaluate each of these in the first derivative. So the first derivative at -1, said you can use whichever version you prefer. So in this case, we'll go back here and use this. So -1 to the third power minus 6 times -1 squared. This is going to give me -4 minus 6 because -1 squared is positive 1, and this is going to be -10. So we know that it's going to be decreasing on the interval from -infinity to 0. So that's what this tells me. So now let's go to the first derivative evaluated at positive 1. So same thing, we have 4 times 1 to the third power minus 6 times 1 squared. And this is going to be 4 minus 6, which is also a negative number. So what happens here is my function decreases and then it continues to decrease. So if you want to draw lines through here to kind of indicate what's happening. It's decreasing and it's still decreasing. What this tells me is that I am not going to have an extrema, no relative maximum or minimum at x is equal to 0 because there is no change from decreasing to increasing or increasing to decreasing. So let's move on and evaluate the first derivative at x is equal to 2, my final test point. And so I'm going to have 4 times 2 to the third power minus 6 times 2 squared. And so this is going to give me 4 times 8, which is 32, minus 6 times 4, so that's going to be 24. Once again, it doesn't really matter what the actual value is, but it is positive, and so that tells me that my function starts to increase. So there is a change here at 3/2. So at the point 3/2 negative 27/16, I am going to have a relative, hopefully you said minimum, because it changes from decreasing to increasing. Now, what's going to happen at x is equal to 0? So we said that there's no change here, so let's go see what happens in the second derivative. So the second derivative is usually where we find our points of inflection and our concavity. So let's find that second derivative. So that's the next thing we're going to do. So from our first derivative, we get that the next derivative is 12x squared minus 12x, and we're going to take that second derivative and we're going to set it equal to 0. So 12x squared minus 12x is equal to 0. I can factor 12x out of both of these, leaving me with x minus 1. And as I set each of these factors equal to 0, I'm going to get my two critical values from the second derivative, and they are going to be x is equal to 0 and x is equal to 1. Notice that the 0 is the same 0 that we found here. So that tells me it's probably going to be that inflection point. So we're going to start by just going ahead and listing that ordered pair 0, 0, and then we'll check the concavity. Let's go ahead and find the second ordered pair here. It's probably going to be a point of inflection, but we'll make sure. So we find that second part. We're still going to be graphing these points because something is happening here. So I have 1 to the 4th power minus 2 times 1 to the 3rd power, and this is going to give me 1 minus 2, which gives me a y value of negative 1. So those are my 2 points that I need to check. So now I'm going to put these two critical values, the x values, on my second derivative number line. So second derivative number line, my 0 and the 1, and I'm going to select some test points on each of these intervals. So let's go with negative 1, positive 1/2, I know you don't like fractions, and maybe positive 2, and these are all going to go into the second derivative, and let's evaluate the second derivative there. So once again, I can use the factored form, or I can go back here. We can use 12 times negative 1 squared minus 12 times negative 1, kind of walking you through all of these pieces. 12, and this is going to be plus 12, and this is going to give me a positive 24. So it's positive here, which tells me that my function is concave up. All right, so then my second derivative evaluated at 1/2, little bit messier. So I have 12 times 1/2 squared. It's not terrible. If you need to plug this into your calculator, you can do so. 12 times 1/2. 1/2 squared is 1/4. 12 times 1/4 is going to be 3 minus 6, which gives me negative 3. Most importantly, it is negative, which means my function is concave down here. So we're going to move right down here, kind of running out of space here, but that's okay. The second derivative evaluated at 2 is going to be 12 times 2 squared minus 12 times 2. This is going to give me 12 times 4, which is 48, minus 24. And once again, I'm going to get a positive 24. More importantly, the fact that it's positive tells me that my concavity changes yet again. So both of these x values are going to produce those points of inflection. So both of these are inflection points. So our points, we have 2 of them, of inflection. We have 2 of those. And so we are going to get ready to graph this and see how all of this fits together. So I'm going to scroll down the screen just a little bit so I have a little bit of space to graph here. So I'm going to draw my x-axis and my y-axis. Here's y, and here's our x-axis. And we're going to try to plot some of these points on here. So these are the 3 points we're going to plot. We're going to plot 0, 0, 1, negative 1, and this 3 halves, negative 27/16, or this negative 1 and 11/16. So we're going to start here with our 0, 0. That's pretty nice to graph. And then we can go ahead. I'm going to kind of pull this out just a little bit, 1 and 2, to give us a little bit of space here. 1, negative 1 is going to be another point of inflection. Here's negative 1 on our y-axis. And then positive 3 halves. Here's positive 3 halves. And then here's going to be negative maybe 27/16, somewhere along in here. We know that this is a minimum, and we know that this is not a maximum. So my graph, you're just going to have to bear with me just a little bit. It's going to come down, and it's going to curve because it was concave up, and then it kind of twists through here and becomes concave down. And then my changes again, becoming concave up through this point, and then it opens all the way back up here. So you get a little bit of an idea. Sorry, my graph is not perfect, but I think you get the idea that it twists through here. And so that's what my graph is going to look like. So hopefully that gives you a good idea how to work that problem, and we will be moving on to the next problem in just a second. All right, problem number 8. We're going to do exactly the same thing. So we're going to start with our first derivative here. So our first derivative of this function is 4x to the third, and then minus 12x squared. We can set this equal to 0 to find our critical values. So 4x to the third minus 12x squared. This is set equal to 0. We do have a greatest common factor of 4x squared here, which is going to leave me with an x minus 3. And I can set each of these equal to 0. All right, so as we take each of our factors and we set them equal to 0, we get, again, a factor of x is equal to, a critical value of x is equal to 0, and we get a second critical value at x is equal to 3. So again, we will take those and we will put those on our number line. We're getting very good at this now because you've done these several times. So I promise you the next one will be a little bit different, but once again, I said we'd like to give you several examples. A little bit repetitive, but better to have too many examples than not enough. So test points, negative 1, 1, and possibly 4 would be good ones. And we'll take these and plug these into our first derivative. I think I'd like to plug in a number rather than just x. So f prime of negative 1. This is going to give me, I'm going to plug them in here, so I'm going to have 4 times negative 1 squared times negative 1 minus 3. This is going to give me a positive 4 times a negative 4, which gives me a negative 16. So it looks like my function is decreasing on this interval. So, and then the next one is going to be f prime at 1. So I'm going to have 4 times 1 squared and 1 minus 3. So I'm going to have 4 times negative 2, which is negative 8. So it is also decreasing. So again, I have a decreasing. What do you think's going to happen here? Think. We'll probably find it to be a point of inflection, but we'll find out for sure in a minute. So the first derivative evaluated at 4 is going to again be 4 times 4 squared and 4 minus 3. We don't even have to work this out if we don't want to. It is going to be 64, but you know you've got a positive and a positive and a positive. Everything's going to be positive. So it looks like I'm going to be decreasing and then increasing. So let's talk about these points real quick. Like I said, you can actually find these points anytime you want to. At 0, 0, or at 0 when we plug 0 in for x, we're going to have 0 minus 0 plus 10. So I'm going to have the point 0, 10. We think this is going to be a point of inflection. It is most assuredly not going to be an extrema. So the next one is what happens when we plug 3 in. And so when we plug 3 in, f of 3, see if we can do some math here. This is going to be 81 minus 4 times 27 plus 10. So we're going to have 81 minus 108 plus 10, and that's going to give me negative 27. And so I'm going to end up with a y value of negative 17 here, which is going to be my relative, hopefully you got this by now, minimum, because it decreased and then it increased, and that's what's happening here. Okay, so let's go to our second derivative, see what's happening there. So our second derivative of this function is going to be 12x squared minus 24x. We're going to set that equal to 0, so 12x squared minus 24x is equal to 0. We can factor 12x out of both of these. That's going to leave me with an x minus 2. And so I'm going to get two critical values, one where x is equal to 0, because when 12x is equal to 0, x will be equal to 0. And I'm going to get a second critical value from my second derivative when x is equal to positive 2. Again, we can go ahead and find those ordered pairs. We've already found this first one. It is 0, 10. This kind of confirms that it's probably going to be that point of inflection, but we'll make sure. So 2, we're going to take 2 and plug it in for x. So f of 2 means we need to raise 2 to the 4th power, multiply 4 times 2 to the 3rd power, and add 10 to it. Lots of practice plugging these back into the original function. This is going to be minus 32 plus 10. So it looks like I'm going to have negative 16 plus 10, or a negative 6. And so when I put these on my second derivative number line to check and see what happens with the concavity, second derivative, here's my two critical values, 0 and 2. Test points, negative 1, positive 1, positive 3. Make very nice ones. Second derivative evaluated at negative 1. If I plug that in here, I have 12 times negative 1 times negative 1 minus 2. It's going to give me a negative 12 times a negative 3. That's going to be a positive 36. So my function is concave up on this first interval. The second derivative evaluated at 1 is going to be 12 times 1 minus 2. So that's going to give me a negative 12. The function is concave down on that second interval. And then finally, the second derivative evaluated at 3 is going to be 12 times 3 times 3 minus 2. And that's going to give us positive 36, telling us that on this interval from 2 to infinity, the function is concave up. So we indeed do have two inflection points. So both of these are inflection points, so two of those, because we have an inflection point anytime we have a change in concavity. So now we're going to sketch the graph of this function and put a whole bunch of things together. So our y and x axis, graphing these very exciting points here, 0, 10. We'll put this one up here. Let's say here's 10, so we'll call this the point 0, 10. We're going to graph the point 3, negative 17, which will be down here somewhere, and then the point 2, negative 6, which will be approximately here. Once again, we do not have but one turning point, and that is this point here. So we do know that the concavity changes. The function is concave up until it gets to this point here. It changes and becomes concave down through this point. And then very subtly there's a change to opening up again and actually curving and doing something like this. So that is going to be our final graph. So very, very similar to the previous one, but once again, it doesn't hurt to get one more example. Okay. All right, let's move on to the next one, which is going to be different. And so this is not a polynomial function, it is a cube root function, something to the 1/3 power. So we are going to have to worry just a little bit about places where the derivative is not defined. So we'll start once again with finding the derivative of this function. So the first derivative of this function is going to be 1/3 times 2x minus 5. This is now to the negative 2/3 power times the derivative of the inside, so we have 2 here, plus the derivative of 1, which is 0. So that's not going to be quite so much trouble. We're going to go ahead and find the second derivative while we're at it here, because I want to redo that first derivative, but let's go ahead and find the second derivative while we're talking here. So the second derivative of this function, clean this one up just a bit here. So this is going to be 2/3 times 2x minus 5 to the negative 2/3 power. We'll leave that alone. And so let's use that to find the second derivative. So this is going to be a negative 4/9 times 2x minus 5 to the negative, subtracting 1 again, 5/3 power, times the derivative of the inside, which is 2. So this is now going to become negative 8. And then I'm going to put in the denominator 9, and I'm going to rewrite this as the cubed root, or I don't guess it really matters, 2x minus 5 to the positive 5/3 power. It's a little bit messy there. So let's go back and look at our first derivative. This is going to be 2 over, and we can write this as 3. We'll probably be using our calculator for a lot of this, so we can leave this as the 2/3 power or the cubed root of that squared. Okay, so let's talk about critical values. So there is no way to make this fraction 0, and that's how we would typically find critical values. We can also find critical values by where the derivative is undefined. Well, the derivative is undefined if the denominator is 0. So we're going to find critical value here by taking simply 2x minus 5 and setting it equal to 0. Right? And so this is going to give me a critical value of positive 5/2 or 2.5, 2.5. So that's going to be my critical value. So let's talk about the number line for the first derivative. That's the only critical value we have. This one's going to be, like I said, I promised you a little bit strange and different, so we're out of the boring stuff here. So 5/2 is my critical value. My test points are going to be 0's always a lovely test point, and maybe let's go with 3 because that's on this side. Let's go back and talk about our first derivative. If you notice anything kind of strange about this derivative, my numerator is positive because it's just a constant. The denominator is a positive constant times this expression that is raised to the second power and then found the cubed root of. It doesn't matter what I do with this problem. When I plug in 0, if I plug in any number, it's not going to matter, but I'm going to show you this. So if I plug in 0, I have 2 over, and it's going to be 3 times, that's going to turn that into negative 5 squared, and then the cubed root of this. So if I square negative 5, that's going to be a positive number, and then I take the cubed root of it, it's going to be a messy fraction, but it's going to be positive. If I plug 3 in, it's going to be positive. We had one of these earlier in I think it was 3.1, where both of these, everything turned out to be a positive value because I had a positive number here and it was squaring here. So what happens here is I have 2 intervals where the function is increasing. So there is no extrema for this function. So this function has no relative extrema because there is no change in the increasing and decreasing. It's increasing all the way through. It actually increases right through that point because the function's defined there. We're also going to get the same critical value from the second derivative. So we're going to talk about what that does to the concavity. Once again, I'm going to take my denominator of 2x minus 5 and find I have a critical value of 5/2 for my second derivative. For the same reason, it's where my second derivative is not defined. If I put this on a number line, Now this one's a little bit different, so my second derivative, here's 5/2, and if I pick a point on either side of this, let's say I can pick the same 2 points, 0 and 3. What happens here is this is an odd power. So whatever number is going to go in here is going to turn out to be an odd number. Or it's going to be not an odd number. It's going to be, if it's negative, it's going to be a negative, and if it's positive, it's going to be a positive. So if I find the second derivative evaluated at 0, I have -8, which I can't change. I have 9. I have -5 to the 5/3 power. Well, this is going to be a negative number divided by a negative number, which is going to be positive. And that's why I said, please don't get so bogged down in the actual numbers. You can plug that into your calculator if you don't believe me, but it is going to give you a positive value. The second derivative at 3 is still going to have a -8 in the numerator, a 9, and then in the denominator, it's going to have 6 minus 5, which is a positive 1. It doesn't really matter what power we raise that to. I'm going to get a negative number. So it is concave up on this interval and concave down on this interval. So at the point 5/2, so when x is 5/2 and y is something, I'm going to have an inflection point. No maximum or minimum, but an inflection point. Now what happens when I plug this 5/2 in? Notice that it's that same 2x minus 5. So if I have 2 times 5/2 minus 5 raised to the 1/3 power plus 1, remember our original function, this is going to be 0 plus 1. And I'm going to get a y value of 1. So this is actually my point of inflection. So let's talk about what the graph of this looks like. We only have one point to graph, and we'll talk about that. So let's graph this point. Here's 1, 2, 3, 1. So here's 5/2, 1. Here's this point, okay? It's not changing. It's not a maximum. It's not a minimum. The function was concave up on this side and concave down on this side. We do not have a relative extrema. So what do you think the graph looks like? And here's what the graph looks like. Kind of, sort of. It's kind of twisty in there. But here's where your point of inflection is at this point 5/2, 1. And it's going to come along, it's concave up, and then it becomes concave down. So nice enough, and that's really all you have to know, and it does increase all the way through here. Okay, so enough of those messy problems. Let's just talk about what graphs look like. So we want to sketch a graph. We did some of these in section 3.1, so not terribly unfamiliar, but just some different characteristics. Think about what happens if you have a function where the function is concave up at this particular point, it is concave down at this particular point, and has a point of inflection at this ordered pair. So that's all we know. So if it's concave up at this point, concave down at this point, and has a point of inflection. So let's sketch the graph and let's plot those points and see what we can come up with. And your graph may not be exactly like this, but this will give you an idea of what kind of thing you should have. So we'll start with the point 5, 4. So we are going to come, well, we'll come all the way out here, 4, 5, 6, 7, 8. I always like to give you like at least 1 or 2 more points than we need. So, all right, so 1, 2, 3, 4, 5, 6, 7, 8 up here, and 1, 2, 3, 4 down here on the negative part. So, all right, so we've got the point 1, -3 is going to be 1 point, and 5, 4 is going to be a point, and all the way out here at 8 and 7 is going to be a point. So we know the function's concave down. The only thing we know for sure, we don't know whether this is a maximum or a minimum. We don't know whether this is a maximum or a minimum, simply know that it is concave down, concave up. So if it was concave down and this was a critical value, then we would know we had a maximum. If this was concave up and we knew x was equal to 1 was a critical value, we would have a relative we would have a relative minimum. But we don't know that. We do know that the concavity changes. We know that it's concave down on this side, so it's probably it's twisting, so it's concave down over here, so it's probably going to look something like this. And so I would probably kind of draw my graph through like this. We know that it's concave up on the other side of this value here, and so I would probably draw something that looked like this. That is a perfectly acceptable graph. You could have a completely different looking graph if you knew some more information. This will be just kind of a little bit of a sketch here. Here's my 0.54 that's going to be my my point of inflection. Maybe if I knew for sure that the function was concave down here, it might look something like this, and we could have another point here, and it could come all the way down here, and it might turn back around. All we know is kind of what's happening here. I personally like this graph a little bit better, but there would be nothing wrong with you telling me that this one was true also. Okay, so you're going to have multiple choices, things to choose from, and ask which of these graphs has these characteristics. Okay, and there'll only be one that's correct. This one tells me some great information, and I love this question, and you're going to see this question again, and I want to tell you what each one of these pieces means. The first thing we do when we see a problem like this that tells us a whole bunch of information is we look for the F of. So this here and this statement here tell me about a point. So this tells me that I have an ordered pair on my graph where x is -3 and y is 8. And this one tells me, you guessed it, that we have an x is equal to 2 and y is equal to 1. Those are points. Now, what does this other stuff tell us? Well, what it tells us is that at -3, the first derivative is 0. So this tells me that at x is equal to -3, there is a critical value from the first derivative. That's what the derivative being 0 is. The fact that the critical value from the first derivative makes the second derivative negative, this tells me that the function is concave down. So we have this point, -3, 8, where x is a critical value from the first derivative, and f prime of -3 is, or f double prime, is negative, which means that it is concave down, which makes this point, you guessed it, opening down, a relative maximum. And that's what we're finding out from this. So now what do we get from the second part of this? Oh, I missed a point. We'll come back and talk about this one. So we've got a third point here, sorry. We also have the point 9, -6. So we have 3 f ofs. Okay, so let's talk about this one. So let's talk about 9, -6. 9, -6, we don't know anything about the first derivative. Absolutely nothing about the first derivative. All we know is that at the point 9, -6, this function is concave, positive, up. And we know nothing about the first derivative for this second point. So this second point 2, 1, oh, but we do know that at 2, the second derivative is 0. So this is a very possible point of inflection. So let's see if we can make a graph that incorporates all of this information. So let's sketch this graph. So we're going to graph those 3 points. So we're going to start with -3, 8 is going to be approximately here. We know that it's a maximum, so it's going to go up and it's going to come down. We know at 2, 1, we have a possible point of inflection, and we know out here 3, 4, 5, 6, 7, 8, 9, -6, the function is concave up. So we know that it's concave down at least through here, and we know that this concavity changes, and we do know that it's concave up here. We don't necessarily know anything else about it, so I'm thinking that since it's concave down, and this is going to change, we're going to make it come here, and then all of a sudden it's going to become concave up, and our graph is going to do something like this. And that's really pretty much all we can get from that. So looking for these key things, the f-ofs give us our points, the first derivative being 0 gives us critical values, along with the second derivative being positive or negative can tell me what kind of critical value, and then the second derivative being 0 tells me points of inflection, pretty much so. Okay, all right, we've got one more. And this is a little bit more of an application problem. So number of visitors to a website in a given week over a year when your period is given by this function. So we're giving you this function where t is the number of weeks from 1 to 0. So no 0 weeks here, I mean 1 to 52. So this is over a year, so 52 weeks. Over what interval of time is the number of visitors increasing or decreasing? Well, this is asking us to start with the first derivative. So we're going to find the first derivative and find some information about that. So let's start with the first part, and we're going to find p prime of t. Now for this particular problem, we are going to have to use a product rule to find this derivative. So we're going to have the derivative of 120 is 0, and so then our product rule says we take the first part, which is our t minus 85, times the derivative of the second part. So that's going to be the derivative of that exponent, 0.02 e to the 0.02 t power. And then plus, because I have a product rule, and I have the second function, 0.02t, times the derivative of the first function, which is just 1. So it's really not as bad a derivative as we think it is. So we're going to start by factoring out the e to the 0.02t power. That's going to help greatly. That's going to leave me with a t minus 85 plus 1, oops, excuse me. We'll backtrack on that just a second. So that's going to leave me with 0.02 times t minus 85, and then plus 1. And we're going to clean this up just a little bit more, so 0.02t, and this is going to be 0.02t minus, and we're going to use our handy dandy. All right, so we're going to use our calculator to multiply that through, and we get minus 1.7 plus 1. Cleaning up one more time. I know this is a very messy derivative, but it's kind of a real-life application. So 0.02t, and then minus 7/10 or 0.7. Okay, so this is what we're actually going to set equal to 0. This is our first derivative. Are we going to get critical values from this e to the 0.02t power? Absolutely not. So this is not going to give us any critical values. So no critical values from this one. We talked about that at the beginning. So the only one we're going to get a critical value from is this one set equal to 0. And if we add 0.7 to both sides and then divide both sides by 0.02, we get t is equal to 35. The first thing we want to check is it's between these two numbers, and it is. Okay, and so now we're going to put that on our number line, and we're going to talk about what this actually means and what it does. So my p prime here, this is my first derivative number line, 35 is going to go over here. Values in either interval, 1 is fine over here, 40 is good over here. It doesn't really matter as long as you plug something in. So I'm going to evaluate not at 0 but at 1. So I'm going to plug this in here. This is going to give me 0.02. This is going to be a positive value, by the way, because anytime I plug something into e, it's going to give me something positive. And then 0.02 times 1 minus 0.7. This is going to be a negative value. Okay, so I have it is decreasing on this interval, and we'll talk about that. And so then the second part, the first derivative evaluated at 40. This is also going to be, we can plug this in, but this is going to be a positive value still. Don't get bogged down in those numbers. 0.02 times 40 minus 0.7. This is going to be a positive value. If you want the actual number, then you can plug that in and get that actual number, but it is going to be a positive value. So what happens is that so we can make a statement down here from 1 to 35 weeks, the number of visitors to this website is doing what? It's negative here, so that means it is decreasing. At 35 weeks, we hit the minimum. So at 35 weeks, we realize the minimum number of visitors. So the minimum number of visitors, number of visitors. And then from 35 weeks to the end of the year, or to 52 weeks, the number of visitors increases. So the number of visitors increases. Why? Why do you think this is happening? Well, it could be that nobody was interested, and then all of a sudden, people started talking about this. Visitors started declining. Maybe they posted something really cool on the website, and people were like, "Hey, that's really fun," and so they started watching again, or started visiting the website. Lots of different things happen. It could just be interest. It took a while for interest to get, people to get interested. Lots of different things. But that's what we're doing. That's where we're finding that. If you wanted to actually find the number of visitors to the website, we would plug 35 back in here, and that would actually give me the actual number of visitors. But at this point, we are good to go. So that is the end of section 3.2. I hope you have enjoyed this lesson, and looking forward to section 3.3.